Now I want to look at exponential decay models. Exponential decay models look basically the exact same as the growth models. The only difference here is that our k value, it's going to be negative. So the exponent is going to be negative, and that's what's indicating a decrease instead of an increase. And so examples of where this might come into play are like drug concentrations in a bloodstream. So for example, if you take a medication, usually it hits the bloodstream with the highest dosage, and then over time, the concentration of that medication in your bloodstream will decrease, typically following the exponential decay model. Another time where we might use exponential decay models is with carbon dating. When something is living, it's basically absorbing the carbon that's in the atmosphere, but then when it dies, and this can apply to even things like plants as well, then it is no longer absorbing the carbon, but that carbon is decreasing. If you were to discover an old item, you would test the amount of carbon that's in that item, and that would be able to give you an approximation of how old it is. So carbon dating also follows the exponential decay model. And so what you see a lot of with exponential decay models is this idea of half-life. And so what half-life is, it's the time it takes for the amount to get cut in half. So let's say if we think about the drug concentration, so let's say at the initial time, the concentration is 50 milligrams. If we know for that specific drug that the half-life is 10 hours, that means we would expect that after 10 hours, the dosage would get cut in half. So for this example, that would mean 10 hours later, there would be only 25 milligrams. And this let's look at an example. Radioactive iodine-131 is a byproduct of certain nuclear reactors. On April 26, 1986, one of the nuclear reactors in Chernobyl, Ukraine, a republic of the former Soviet Union, experienced a massive release of radioactive iodine. Iodine-131 has a half-life of 8 days. So what is the relative decay rate for iodine-131? So this is if we think about the model. And honestly, so to help me not get mixed up, sometimes I don't actually, to help myself not get mixed up, sometimes I actually don't put a negative in front of the K, but I know that when I'm dealing with decay, that I need to make sure that the value that I end up with there is going to be negative. So to define the decay rate, we actually don't need to know any values because we can really plug in any numbers for the amounts using the half-life, and we'll get the correct decay rate. So what I mean by that is, let's say, when t is equal to 0, n of t is, this is where I'm just picking a value, 100. So if the half-life is 8 days, that means 8 days later, the value would be cut in half. So then I could call this 50. And I haven't even put units here because it doesn't matter. I'm just using this calculation to figure out what the K value is. So let me go ahead and plug in all this information. So first, maybe I'll write the equation with just 100 in that initial place, the initial value. just kind of as a placeholder. And then I'm going to plug in information about 8 days later. So that tells me 8 days later it's going to be cut in half. So the final amount is 50 after 8 days. So I'll plug in 8 right here. And then I can go ahead and solve for K to find the decay rate. So this is kind of why it doesn't matter what values you plugged in, because at this point I'm going to divide both sides by 100. So I end up with 1/2 is equal to e to the 8k. And so no matter what values I plugged in, as long as the second number was half of the first, it's always going to end up as 1/2 at this point. So if you're using half-life to figure out the decay rate, it'll always end up looking like this at some point in your solving. So now to keep solving further, we could take the ln of both sides. So I've got ln of 1/2 is equal to, basically on the right side, the ln and e are sort of canceling out. So that leaves 8k, and then the last step is to divide by 8. So k is equal to ln of 1/2 divided by 8. And I'm going to go ahead and plug it into the calculator. And so what I found is that the decay rate is negative 0.087, and also confirming it's a negative, which is what I would want for a problem like this. So that's good. So that's the decay rate. The next question we have here is, how long did it take for the iodine 131 to reduce to 42% of the original amount released after the explosion? Round to the nearest day. So let me go ahead and write the model again. And I'm not going to leave the 100 there because that wasn't actually the initial value. And we still don't know the initial value, but I'm going to go ahead and write the model with just leaving the n sub 0 there and filling it in with our k value that we just found. So that's negative 0.087 t. So this is what our model looks like. So we're trying to figure out how long it's going to take to reduce to 42%. So before I do any calculations, I mean, one thing I might mention is that I know based on the half-life that it is going to take longer than 8 days. Because 8 days is what it would take to get to 50%. So sometimes I like to just think about that ahead of time, so when I get my answer at the end, I can kind of see, does it make sense from what I expected? Okay, so what could we do at this point? Since we don't know the initial amount, there's a couple of things that we could do. I could actually plug in another value like I did for part A. So in this case, let me go back to 100 again. And if I want to know when it gets to 42%, well, what is 42% of 100? That's going to be 42. And I could go ahead and solve this equation for t, and that will give me my answer. If you don't want to plug in a random-ish value like the 100, you could actually leave it as n sub 0. And I'm realizing here I forgot to put an extra 0 there, so it's negative 0.087 t. So if I leave the n sub 0 alone on the left, if I'm trying to say, I don't care what the original amount was, that's just n sub 0, but it needs to end up being 42% of that, I could write that as 0.42 times n sub 0. So that's saying whatever the original amount is, I'm finding 42% of that original amount. The reason it doesn't matter which way we would go in a problem like this is if I look at the first one with the 100, if I divide both sides by 100, that leaves 42 divided by 100, which is 0.42 equals e to the negative 0.087 t. If I look at it in that other version I have, I could divide both sides by n sub 0, and that cancels out, leaving on the left just a 0.42, which is the equation that I have. So as long as we're ending up at that place, then we're good to go. And so here I just need to solve for t using the same steps that we just used in the first part to solve this exponential equation. So I've already done the division, so now we can take the ln of both sides. So that leaves ln of 0.42 is equal to negative 0.087 t, and the last step is to divide. So I've got t is equal to ln of 0.42 over negative 0.087. And I'm going to plug that into the calculator. So when I plug it in, I get about 9.97. And here it said to round to the nearest day, so I would round that up to 10 days.